Cool. Hello everybody. Today I have the great pleasure to introduce to you Philip Mocz, currently at Princeton University. And in the next, 45, 50 minutes or whatever, he will give you an update on his recent work on the first structures in fuzzy dark matter.
Thank you, Bodo, for that introduction, and welcome everyone to my talk. Today I'll talk about simulations of first structures in fuzzy dark matter, both the gas and the baryons, and how the fuzzy dark matter contrasts with other dark matter models, including cold dark matter and warm dark matter. So let's begin. I'll start by, in this outline of my talk, I'll start by first describing both motivations for the fuzzy dark matter model, and some recent observational tensions. I'll also motivate new probes for studying fuzzy dark matter and placing constraints on the particle physics. And I'll delve right into full physics cosmological simulations of fuzzy dark matter, where my main argument will be that the formation of first galaxies in the universe at around redshift 6, low mass galaxies, are a very unique probe for the physical nature of dark matter, in part because they are not yet fully virialized, and they trace some of the initial conditions in the power spectrum. And this is an excellent test. The detection of the structure of first galaxies will be an excellent test to that can be observed with the upcoming James W. Webb Space Telescope. And I'll talk a little bit about fuzzy dark matter model in the context that the axion mass is large and how it reconnects with classical cold dark matter theory. Then I'll also investigate extensions of the model, most notably adding in the strong CP violation scale into the problem, and how that changes structures such as soliton cores in the fuzzy dark matter model. And lastly, I'll spend just a few slides on just highlighting student works on further probes that can be used to constrain fuzzy dark matter model, and these focus on small-scale astrophysical phenomena and features that are unique to fuzzy dark matter model, that include dynamical friction and heating, as well as interaction of the soliton with the supermassive black hole at the center. And so I'd just like to highlight that this is work done in collaboration with a lot of people, where I've highlighted some of the faculty I work most closely with, and I've highlighted the students in orange, a lot of great students at Princeton. And so to motivate the problem, we of course know that the dark matter problem is nearly a century old by now, and one of the most intriguing mysteries in modern physics, because we do not know the nature of 84% of the matter content in the universe. Yet it is believed to hold galaxies and clusters together and govern the cosmic structure. And there's of course a lot of motivation from the observational side for existence of dark matter, which begins with measurements of the rotation curve in galaxies. The impact of dark matter is important for large-scale structure. Its properties can be inferred from CMB. You can detect it in lensing. And of course, recently discovered ultra-faint dwarfs that possibly possess no dark matter also place constraints on how dark matter behaves. And so today we'll be investigating 3 models for dark matter. On the right-hand side is a classical cold dark matter with WIMP particle on scales of GeV particle mass. And this will be contrasted against fuzzy dark matter on the left, which is an ultralight boson with a fiducial value of 10 to the minus 22 eV particle mass. And intermediate is the warm dark matter with particle masses of keV. So in the fuzzy dark matter model, we're assuming here an ultralight scalar field, 0 temperature in the early universe that forms a Bose-Einstein condensate, and we have macroscopic wave-like properties in the superfluid dark matter. And And importantly, there's in addition to the collisionless cold dark matter theory, in the fuzzy dark matter model, you have an additional quantum pressure term, which one of the consequences is that it suppresses gravitational collapse below the scales of the de Broglie wavelength. And for these ultralight particle masses of 10 to the minus 22 eV, this wavelength can be large, kiloparsec scale, so it would affect astrophysics and cosmology. In the simplest form of the theory, the fuzzy dark matter is governed by the Schrödinger-Poisson equations, where we define the dark matter by this wave function psi, where psi squared is normalized to the dark matter density, and we have the Schrödinger equation where the potential is the self-potential due to the self-gravity of the dark matter fluid. And two key features of this model, there are of course more, but two key features are that we have suppressed small-scale power due to the quantum pressure, and the second feature is that this dark matter model can form large low-density cores called the soliton solution. And so the motivation for the fuzzy dark matter model is multifaceted. Some of it stems from astrophysics, where the model may help alleviate some of the small-scale challenges of cold dark matter. So I'll first of all point out that cold dark matter does an amazing job at describing large-scale structure, meaning that dark matter on large scales is cold and collisionless. But on small scales, it does not get the statistics and shapes right for the dwarf galaxies. And so these include the cusp core problem, where cold dark matter predicts cuspy NFW-like profiles, whereas observations predict large low density cores, and other problems related to the statistics and abundance of the dwarfs. There's also motivation from theoretical physics, where the candidate particle for fuzzy dark matter might be the axion, and the axion historically has been a theoretically predicted particle to solve the strong CP problem. And in this classical version, the mass is on order 10 to the minus 5 eV, and but string theory compactification particle models can provide classes of ultralight axions that are orders of magnitude smaller in mass. And so I've mentioned that predicting cores for satellite galaxies is very important. And so some of the original constraints on the fuzzy dark matter model have been carried out by Dottie Marsh and Roxana Popp in 2015, where they've modeled these dark matter dominated dwarf spheroidals for an extant sculptor with a pure dark matter soliton core profile. And such modeling tends to favor 10 to the minus 22 eV particle mass. On the other hand, well, we also have constraints from the cosmic microwave background, of course, where because of the quantum pressure, you suppress large K initial dark matter power. And so to make sure that you do not wash out all cosmic structure, you need at least a 10 to the minus 24 eV particle mass. Otherwise, you're inconsistent with CMB fluctuations. And then you can further probe the scale of power in dark matter on different scales with Lyman alpha forest. So Lyman alpha forest is ideal for probing megaparsec scale power between redshifts 3 and 5, shown here. And in order to not wash out too much structure with the quantum pressure, the axion mass has to be on order 10 to the minus 21 eV or larger. And so you can already see that there's a bit of a moderate tension in setting the particle mass simultaneously to capture both these large low-density cores inferred from satellite galaxies, and to have the right amount of small-scale of substructure in the universe. And I'd like to point out also that the so as recently highlighted by Andy Burkert and also Mohammed Safarzadeh and David Spergel this year, Just a simple analytic core model cannot simultaneously explain this constant surface density, dark matter surface density inferred from observations for all satellite galaxies. So shown in this plot is a figure from Andy's paper showing this universal surface density of 75 solar mass per parsec squared, and the blue lines represent the predictions for a pure analytic soliton core at a given axion mass. So the highlighted line illustrates 10 to the minus 22 eV, and you can see that it can only explain a subset of the data. Of course, there are reasons why pure analytic soliton core is not accurate is not a complete description of what's happening in all these systems, and that is one of the reasons why numerical simulations are so important to study the fuzzy dark matter model, and really have only been an important an applied tool in the last 5 or so years. So to figure out what's going on with this catch-22 problem, we need simulations to investigate, for example, the possibility of additional nonlinear structure formation on small scales, which might relax some of the conditions from the constraints from the Lyman alpha forest, and also modifications to the soliton core profile in the context of cosmology and of baryons. And so let's begin by talking about some of my recent work highlighting the formation of first structures in fuzzy dark matter. So these are full physics simulations, meaning that these include baryon star formation and feedback, as well as all the quantum wave effects of the fuzzy dark matter theory. We create proper initial conditions at redshift 127 using the publicly available code AxionCam. And the simulations are run at 1024 cube resolution using 5 million core hours on Stampede 2 cluster. And the limitation of the method is that it's quite memory expensive because we need to resolve the kiloparsec scale interference patterns. So we are restricted here to box size of a couple megaparsecs and resolving only the first structures that form at around redshift 6. And here's a highlight of some of these simulations where I'm comparing 3 different theories. So top is cold dark matter, and you can see that there's a lot of substructure. And then in the second panel is warm dark matter-like simulation. And the third panel shows a fuzzy dark matter simulation, where the warm dark matter simulation and fuzzy dark matter simulation have been tuned so that the warm dark matter simulation has an effective mass that's the same as that has the same effect in the initial power spectrum as the fuzzy dark matter simulation does. And so if we zoom in on smaller scales, you can see quite a lot of interesting differences in these filaments. So shown here is a slice through the filaments. And so in the cold dark matter theory, the filament is composed of subhalos on all scales because the theory is scale free and there's no suppression of small scale power. In the warm dark matter theory, you have suppression of small scale power in the initial conditions. So you do not form subhalos below critical mass. Instead, you form these nice sharp caustics. And these caustic features are regularized in the fuzzy dark matter model due to the wave-like nature of the dark matter. And you can see that they become these coherent interference patterns. Now, if we dive a little deeper, we'll see that there's actually more structure. So in addition to interference patterns, we'll have something called soliton cores. But so one thing to point out here now is that I'm highlighting that these simulations also have gas and stars. And I'm zooming in on this filament that forms. And very interestingly, a key when you introduce a cut in your initial power spectrum, the first structures that form are not halos, but extended filaments on scales of megaparsecs. And we can see that the star formation might trace these filaments very closely. And so rather than forming individual galaxies, as is predicted in cold dark matter on the right, these are mock JWST images. We form on the left-hand side in the fuzzy dark matter model and in the warm dark matter model, this continuous star formation along the filament, where these stars eventually will accrete to form individual galaxies. But this is a very stark prediction for what JWST might see if the axion mass is something like 10 to the minus 22 eV. And so we have this collapse of cylindrical filaments. And in the simulations, we actually identified a new nonlinear structure formation channel where these cylindrical filaments are unstable. We found that the core, these filaments have a spine that's supported by the quantum pressure, but this is not linearly stable, and this cylindrical soliton spine can go unstable and form spherical solitons. And so in the cosmological context, this is an additional formation for low mass solitons that are about a couple orders magnitude lower than what you'd predict from linear theory and just taking the cutoff in your initial power spectrum. And so this is one way to ease the ease the tension in the Lyman alpha force predictions, which has to be investigated with further simulations and more statistics. And before I go to the next slide, I'll point out that in these filaments, the stars and gas, when you're comparing fuzzy dark matter and warm dark matter, in the fuzzy dark matter model, the stars and gas trace the chord nature of the dark matter because their gravity here in this case is subdominant. And so looking at the dark matter power spectrum and some of the nonlinear effects, we can see that, of course, we have a dearth of power at higher redshifts due to the initial cut in the power spectrum. But already by redshift 7, we see additional power in the fuzzy dark matter model compared to warm dark matter and also cold dark matter because of these interference patterns on scales of tens of kiloparsecs. And at agreement, and everything's in agreement with cold dark matter above 1 megaparsec because the wave-like features of the model do not affect the dynamics on those scales. So to summarize, for these first structures that form in the fuzzy dark matter model, they are not your ordinary spherical galaxy, but they are elongated filaments, filamentary star-forming structures that, and thus the observation of first galaxies might they offer a unique probe of the physical nature of dark matter, and future missions such as JWST will open an observational window into this emergent world of galaxies and really tell us something about whether dark matter interacts on these with itself on these scales. And I've mentioned that this nonlinear channel for structure formation that can produce low mass solitons a couple orders magnitude below predicted from linear theory can also help ease this catch-22 problem. And finally, I'm just highlighting the basic properties of these first filamentary star-forming galaxies, where the dark matter shows these coherent interference patterns, the stars and gas trace the chord dark matter profile. And so I'd like to just spend a couple slides on the numerical methods that went into these simulations. And of course, there's a lot of numerical methods out there now these days, including particle-based methods and adaptive mesh refinement methods. So we're using here a simple spectral method, which is very easy to implement, but it does mean that we're using a uniform resolution, which is part of the reason why these simulations are so memory expensive. But the method relies on Fourier transforms and applying these unitary operators to maintain exactly important symmetries of the Schrodinger-Poisson equation. So we can simply solve for the gravitational potential with FFTs in equation 2, and then apply this unitary operator half-step kick in equation 3, followed so applying the effect of the potential, followed by a kinetic operator, the drift term in equation 4, and then followed by another kick applied for half step. So this type of implementation makes it very natural. This leapfrog type discretization makes it very natural to couple to most modern cosmological codes. And I'll also point out that the so the numerical method has been coupled into the Arepo code, which is a moving mesh code, and so meaning that the baryons are treated using an adaptive Voronoi mesh, and which means that you can resolve individual galaxies quite well, and the method is quasi-Lagrangian, meaning that you don't have large advection errors. And so I'd like to talk a little bit more about the formal connection between fuzzy dark matter and the equations for cold dark matter, and especially because we've seen that the on scales of omega parsec, these two theories agree very well. So there's this question of how does something like the 3D Schrodinger equation encode similar information to what collisionless dynamics encodes, which has a 6-dimensional phase space, basically a 6-dimensional distribution function. So on the top we have the Schrodinger equation, bottom we have the Boltzmann equation, and in a paper from a couple years ago, we explored the limiting behavior of large boson mass, and basically asking what would the fuzzy dark matter look like if we instead start approaching a mass that's similar to the standard QCD axion mass. And so we found that the 3D wave function can encode information that's in the 6-dimensional distribution function. And even though there's a difference in this dimensionality, this is possible due to the superposition principle that's found in the equations for quantum mechanics, and also the fact that the gravity is long range, is only long range, and there are no short range forces in this problem. And so we have a general way of constructing a wave function given a distribution function by superimposing different wave modes with random phase offsets. And in this plot, we see here this test problem where we're collapsing some initial condition that gives these nice caustic structures in the classical collisionless case, and these caustics can be approximated with interference patterns in the middle panel as you make the axion mass smaller. And importantly, we actually find a formal convergence of the potential to the classical limit as a function that scales as the axion mass to the -2 power. So even though the density field that's being highlighted in the figure shows order unity fluctuations. And so we can also test this convergence in a cosmological context where we're simulating, so here I'm looking at the formation, the most massive halo, and on the left-hand side is a cold dark matter simulation. Right-hand side And then in the middle panel is 10 to the minus 22 eV mass, and then lower mass on the right hand side. And on the bottom, I'm showing the radial profiles of these halos, and we can see that the solution in fuzzy dark matter model starts approaching this classical NFW-like profile that has an r to the minus 1 inner slope and r to the minus 3 outer slope. And furthermore, though, this singularity that's present at the center of the halo is always regularized by a soliton core. So in summary, and so this is something I call the Schrodinger-Vlasov correspondence, where the classical limit for the gravitational potential of the problem can be recovered as with a scaling that goes as the particle mass to the minus 2 power. And importantly, this means that the gravitational forces converge to the classical limit as order m to the minus 1, even though you have this order unity interference patterns on small scales. And this convergence of forces is very important because that means, well, if we're studying dark matter through its coupling to baryonic matter, then the behavior of that baryonic matter will approach cold dark matter like behavior in the limit of large axion mass. And so another key feature, of course, is where the solutions differ is that these caustic singularities, like the centers of halos, get in cold dark matter are always regularized because of the quantum pressure and by these soliton cores. And fuzzy dark matter halos in the outskirts of the soliton core are NFW-like. And so I think the place where a lot of effort is needed for the future is to really now create larger samples, statistical simulations to get more statistics on the range of possible structures that you can form in the fuzzy dark matter model. And so if one wants to take that route, the best way to do it may be with approximate particle-based simulation methods rather than using a fixed grid spectral method. And to resolve the, so there's a second area that I'd like to focus on for the rest of the talk, which is to go a little bit further and add a bit more particle-specific physics into the model. So we're talking about this ultralight fuzzy dark matter limit where the particle mass is very small, and it can be in general any boson. But if it's in particular an axion, then then this axion particle will have will break the strong CP symmetry at some scale, and this will actually modify the Schrodinger-Poisson equations, which I'll get into. So one of my current goals is to introduce the second parameter in the problem, and then ultimately be able to constrain both the particle mass and the strong CP symmetry breaking scale using the known observations, which include Lyman alpha and constraints from gravitational lensing, stellar streams, etc. So if we return back to this catch-22 problem, I'll try to motivate why attractive self-interaction might help resolve it. But of course, there are other resolutions. One that we must all be aware of is that dark matter might simply not be fuzzy. And in that case, it's very important to rule it out the best we can. And I've already mentioned that based on the simulation work that I'm that there's based on my simulation work, there's already ways that the catch-22 tension is being eased For example, we're forming substructure below the exponential cutoff scale due to the nonlinear instability. And then baryonic physics and feedback also has to be taken into account. But let's take a look at the strong CP symmetry breaking scale and how that modifies the problem. So our starting point is this action where we introduced classical cosine-like potential for the axion, and this has been I'll just mention this reference by Desjacques, which points this out that so taking some fiducial value for the symmetry breaking scale like 10 to the 17 GeV, and this coupling constant is tiny in dimensionless units, but nevertheless it can still affect cosmic structure. And so if you start with the action in equation 9 and work out the non-relativistic limit, you obtain the Gross-Pitevsky Poisson equation, where now this difference is this new attractive self-interaction term that you've introduced, which so it's important. So it scales as the density of the dark matter, and this minus sign is very important. So this attractive self-interaction can be characterized by this effective S scattering cross section, which ties back directly to this F, your decay constant. And so currently we are looking at what happens to these fuzzy dark matter halos as we are increasing the self-interaction strength. And this is work in progress currently in a summer program at Princeton by a brilliant undergraduate, Noah Notice, where we're able to demonstrate this transition, this phase transition that takes place in the central solitonic core, where if the self-interaction is very small, the soliton is largely unmodified, but above some critical value, as we increase the self-interaction, this soliton goes unstable and collapses into a very compact object. And the goal of the summer project will be to create halo profile models for this case on the right-hand side where the soliton has collapsed. And in terms of a cosmological context, we can see that if the self-interaction is again made strong, then you can form additional small-scale substructures. So on the top, I'm showing a fuzzy dark matter model with zero self-interaction, and I'm slowly increasing it. On the right top two panels, and we see that on the right-hand side, we formed some dense solitons in the in the cosmic structure, and this is very different type of substructure from cold dark matter, which is seen on the bottom. And I'm just highlighting how the relative power spectrum shows an increased power on these small scale compared to the zero self-interaction case. So I think this is a very promising avenue to explore to resolve the catch-22 problem. Currently, these simulations are in progress, running on the Dirac cluster at Cambridge over the summer, and I'm hoping to have results soon. And so just in the last few minutes of my talk, I'd really like to highlight that one of the unique features of fuzzy dark matter is that it does predict a lot of small-scale wave-like substructure, which can be tested on with a variety of different methods. So I'll highlight this recent work led by two students, Lachlan Lancaster and Kira Giovanetti at Princeton, where we, in this paper, we studied with simulation and analytic theory, both this the dynamical friction that is experienced in fuzzy dark matter. And in many cases, the dynamical friction is largely reduced from what you'd predict in cold dark matter. And this can solve some of these well-known problems, such as satellite infall timing problems. It might also have some implications for the final parsec problem in helping supermassive black holes coalesce faster if they each have their own soliton core about them. But we also were able to identify in this paper 3 different regimes where the fuzzy dark matter dynamical friction actually acts differently. So these different regimes depend on which forces dominate, whether it's gravity versus quantum pressure in the fluid or the velocity dispersion, and or some mixed model. And so there are instances where the velocity dispersion in your background fluid can dominate, and in that case, the perturbing object can experience a random walk when traveling through this background medium with some relative velocity. And then there's also case where you have zero velocity dispersion, where in the classical case, you'd actually predict no dynamical friction, but because of quantum pressure, you form this quantum wake, a wave-like wake, which is shown in this movie, which is an additional source of dynamical friction in this regime, whereas you'd predict none in cold dark matter. So there are other small-scale effects that might be interesting to consider, and one is, as I've sort of alluded to, how do soliton cores get distributed around supermassive black holes? And first of all, I'll point out that these soliton cores are zero angular momenta solutions, and by the no-hair theorem, they cannot exist forever around supermassive black holes, but they can exist for in a quasi-steady state for a very long time, like comparable to the age of the universe if the axion mass is small enough. And so in the case of so with the summer student a year ago, we worked out what the soliton core might look like in our own Milky Way, where we have and also M87, where there's a very massive supermassive black hole, much more massive than the soliton. And this is important because it reshapes the soliton, makes it more compact, and we have very good limits on how much dark matter can be packed into close around the black hole from a variety of observations. So using these models, so we found that the soliton is reshaped into a hydrogen Bohr-like solution about the black hole, so an exponential profile, where the size of the core scales inversely with the black hole mass. And with these new analytic models for what the soliton core looks like in the presence of a black hole, we were able to rule out a narrow range of axion masses, which would violate observations of how much dark matter could be close to the recently imaged M87 by the EHT. And finally, I'd like to point out this that the interference patterns in the dark matter halos also lead to dynamical heating. And so with a student, Ben Church, we worked out what this dynamical heating might look like in the Milky Way as a function of the dynamical heating of stars that are coupled to the fluctuating dark matter, how that would look like as a function of axion mass, and how the old stellar disk in the Milky Way, how its velocity dispersion would increase over cosmic time because of this heating as a function of radius. Well, we see that the heating is most effective at the center of the galaxy, and at large radii, you have another source of heating, which is due to subhalos. And importantly, it's not shown on this plot, but the observations lie at 30 kilometers per second, which mean that we can rule out axion masses that are above a few times 10 to the minus 22 eV. And so this concludes my talk. I'll just put up one of my earlier simulations of where we're merging soliton cores and forming quasi-stationary, quasi-steady state dark matter halos, just to highlight these fluctuations that you have in the dark matter field that are responsible for the heating. Okay, so that concludes my presentation for now, and I'm happy to take some questions.
Yes, very good. Thank you very much for this interesting talk.
Oh, thank you.
Yeah, you were talking about this dynamical friction at the end and heating.
Mm-hmm.
Did you investigate that also for your cosmological simulations with the filaments? Do you see some sort of, I don't know,
yeah.
heating or so also in the baryonic component?
Oh, excellent question. Yes, so I imagine that there, yeah, okay, yeah, so there will be heating. So that was not investigated in detail because we did not have a lot of so we're looking at redshifts down to redshift 5, which is only shortly after the free fall time. So there's still a lot of cosmic time left over which this heating will actually be most important. And then another point of concern is that this dynamical heating is not really resolved in these cosmological simulations where you have star particles that represent hundreds of thousands of stars, and they have smoothing lamps. So it's generally underestimated significantly in these simulations.
Because the stars are simulated too heavy.
Yeah.
So they basically don't care about these interference fringes.
Yeah. But that's
still...
just an artifact of that's just an limitation of not resolving individual stars.
But they can they form as efficiently as in the, for example, the warm dark matter case where you don't have these interference fringes?
Can the stars form as efficiently?
Yeah. So if you say that okay, the stars are the
mm-hmm.
resolution, the star particles were too heavy to actually see something. Can you say something about the
so
star formation if it's altered between these
yes
two?
Oh yeah, okay, yeah, that's a great question. So I did not talk about it in these slides, but I have looked at the star formation, how that's altered between fuzzy dark matter and warm dark matter. And generally the most important thing there is that in the fuzzy dark matter model, you regularize these caustics. So when you have these individual filaments, they have lower central density and shallower potential wells because of the quantum pressure. And this is actually very important. These star formation will be dependent highly on how deep you can make these early deep potential wells. And so the star formation can be reduced by a factor of 2 compared to warm dark matter.
Yeah, and then probably with the fluctuations then on top, those probably reduce the star formation rate then on top of your regularization rate.
That's a great point. So I know that, well, yes. So the only caveat is, of course, we're using a subgrid prescription for star formation. So I think we have a good control on the relative star formation between fuzzy and warm dark matter, but and how relatively it's reduced in fuzzy dark matter. But we can, of course, we can increase the star formation in the fuzzy dark matter models with the subgrid parameters that are unknown.
Are you planning to extend that simulation somehow in the near future, or?
Oh, I hope so. I'd have to double the resolution, and then you could get you can extend it by a scale factor of reducing the scale factor by a factor of 2, and so that's Yeah, I think I could go up to maybe redshifts like 3 or so if I double the
No, but
resolution.
it's a hard task. I know.
It's a hard test, yeah, yeah, and that's why I really like the AMR techniques that you're using, Bodo, because you can then study some small scale features in some larger cosmological context.
Yeah, it's very nicely complementary.
Uh-huh. Yeah, it's
Um,
still difficult because even if you have constant density in, say, a void, if you have a particle-based methods, you don't really need many particles to resolve that. But if that constant density has some velocity, then you have to resolve the wavelength of the phase.
yeah,
Yeah,
that's exactly that's one of the biggest problems.
yeah,
I mean, at some point you typically just say, okay, now the density is so low, I don't care if it's evolved correctly or not.
yeah, yeah,
Just let it get stuck there, basically by not resolving the
yeah.
phase enough, and then just concentrate on the collapsed
Yes,
regions,
yeah. I
and don't
do.
care about the voids.
Yeah, I do see this. When I do not resolve, when things are not properly resolved in this type of simulation, then features actually get stuck in physical space because you cannot
Yeah.
resolve their velocities.
Yeah, that was the first lesson actually I learned doing my
Yes.
PhD. I had a really low resolution run, and I was wondering why nothing happened all the
Yes.
way down to redshift 0, and then I just realized that everything was just stuck due to low resolution.
Yes.
But yeah, that's always the tough problem
Yeah.
especially compared to cold dark matter, where you can just run these n-body simulations so efficiently.
Hmm.
Um, but do you also plan? I mean, you said that the baryons are simulated on this moving mesh.
Hmm.
Do you plan to somehow put also the fuzzy dark matter part on that moving mesh at some point,
Yeah.
or is that also too complicated?
Yeah. That would be an interesting point. So I think it's possible. I mean, if you have, um, yeah, yeah, if you have AMR worked out, then I think, yeah, in theory, it's not much different.
Yeah.
And
Because I think at
so,
some point, for example, um,
hmm,
well, what's his name? Phil Hopkins did that with his
hmm,
Gizmo code.
hmm,
So
yes,
he
yes,
implemented actually fuzzy dark matter routines
hmm,
on his moving mesh.
hmm. That's right.
Which I mean, at least kind of worked.
Yes, yes,
I think
and
he
there's
still has a
there's
hard
also,
time once there is interference. So I think he still has a kind of a hard time in these
yeah,
highly
yeah,
nonlinear
yeah.
regimes.
So
But
these particle-based methods are still in development, but I think there's very nice recent work by Matteo Nori's, Matteo Nori's work, where he's also developed a similar SPH-like
yeah, yeah,
method, and
yeah. The paper
uh,
that just came out
yes,
last
yes,
week or
like,
so.
and resolving soliton cores
Yeah,
in
that's actually
halos,
very
and
interesting. Yeah,
yes, yeah,
I
looking at
had
the
the
scaling.
pleasure to meet him in Munich actually
Oh, that's great.
in February, and we already discussed that work there.
Yes,
Um, and yeah,
yes. So
so
those
I was really
simulations
happy
are a
that that paper is now out
very
and
nice
it looks really good.
complement. Yes, because it gives some of the statistical, um, yeah, it gives some of the statistical power that you need
Yeah,
to predict things like the core mass and the halo mass relation, and
yeah,
yeah, we were actually talking about this earlier, Bodo, about the core mass halo mass relation before I started recording this talk. But that's a that's something that's very interesting um, to to follow up on with simulations, because it's not clear that that relation has to be 1-to-1. It
yeah,
could be a
definitely.
function of formation time of the halo, could be a
Uh,
function of how baryons or feedback the um, reshape the central core. So it could be a function of the history of what happens.
Definitely. I mean, it will be correct by an order of magnitude, but
Yeah.
there could be an order. I don't know. There could be a factor of 2, 3, 4 easily
Yep. And then there's
modifying
also,
that
yes,
relation.
and there's
Uh,
also this slow growth, mass increase in the mass of the
uh,
soliton core, according to the left cup. equations.
Cool. I
Yes.
think before
Okay.
we diverge too far from
Oh, okay. Yes.
off topic, we should probably just stop recording here. And
Okay.
if somebody has further questions, then I guess you will be
Yep.
at least
I'll be
virtually
here.
around during the conference.
Yep. Please get in contact.
Thanks again.
Okay. Thank
And
you.
see you around.
Okay. Thank you.